Welcome to the Nocturnal Astronomer, where we journey through the cosmos under the gentle blanket of night. I'm your host, Atlas Reed, and tonight we're exploring one of the universe's most captivating mysteries. Imagine, if you will, our entire galaxy, along with thousands of neighboring galaxies, being pulled inexorably through space towards something we cannot see. Something so massive and mysterious that it defies our direct observation, hidden behind the dust and stars of our own Milky Way. This is the story of the Great Attractor, a gravitational giant that has been dragging our cosmic neighborhood through space for millions of years at speeds of over 1 million miles per hour. Tonight, we'll uncover how astronomers discovered this invisible force, explore the mind-bending scales involved, and understand what this cosmic journey means for our place in the universe. We'll delve into the detective work that revealed this hidden giant and discover how it fits into the grand tapestry of cosmic structure. If you enjoy these nighttime voyages through the universe, please consider giving this video a thumbs up and subscribing for more cosmic tales. And I'd love to hear from you, so tell me in the comments, what aspect of deep space mysteries fascinates you most? Alright, let's dive in. The story of the Great Attractor begins in the 1970s, when astronomers were meticulously mapping the cosmic microwave background, the ancient light that fills our universe. Think of this background radiation as a gentle glow left over from the universe's infancy, like the warm embers of a cosmic fire that burned 14 billion years ago. As scientists studied this ancient light, they noticed something peculiar. The temperature of this background radiation wasn't perfectly uniform. In one particular direction in space, it was slightly warmer, by less than 1/100th of a degree. This tiny temperature difference might seem insignificant, but it revealed something profound about our cosmic motion. When we move toward a source of light, that light appears slightly bluer and warmer due to a phenomenon called the Doppler effect. It's the same principle that makes an approaching ambulance siren sound higher in pitch. The warmer cosmic microwave background in one direction meant our entire local group of galaxies, including the Milky Way, was racing towards something at an extraordinary speed. The discovery presented a puzzle that would take decades to fully understand. Here was clear evidence of an enormous gravitational influence, yet when astronomers pointed their telescopes in that direction, they couldn't see what was causing it. The mystery deepened when they realized the scale of what they were dealing with. This wasn't just our galaxy being pulled along, but thousands of galaxies spanning incredible distances, all moving in a coordinated flow toward this enigmatic destination. By the 1980s, scientists had confirmed that our entire local group of galaxies was racing through space at extraordinary velocities toward an unseen gravitational source. This invisible force became known as the Great Attractor, named for its ability to gravitationally attract vast collections of galaxies across hundreds of millions of light years of space. The reason the Great Attractor remained invisible for so long lies in an unfortunate cosmic coincidence of perspective. Picture yourself trying to see through a thick forest. Even if something massive exists on the other side, the trees block your view completely. This is precisely what happens when we try to observe the Great Attractor from Earth. It lies directly behind what astronomers call the zone of avoidance, a region where our own Milky Way's disk, thick with dust and stars, obscures our view of the distant universe. The Great Attractor is obscured by the Milky Way's galactic plane, lying behind the zone of avoidance, so that in visible light wavelengths, the Great Attractor is difficult to observe directly. Imagine trying to study a distant mountain while standing in the middle of a dense fog. The dust and gas in our galaxy's disk absorb and scatter light from objects beyond, making direct optical observation nearly impossible. However, astronomers are resourceful. They began using different wavelengths of light that could penetrate the cosmic dust. Radio waves and infrared light became their tools of choice, able to pierce through the veil that visible light could not. Through these observations, they began to piece together the structure of what lay hidden. They discovered not just one massive object, but a complex region filled with galaxy clusters and vast amounts of dark matter. The observed attraction suggests a localized concentration of mass having the order of 10 to the 16th power solar masses. To put this in perspective, imagine the mass of 10 million billion suns concentrated in a relatively small region of space. This enormous concentration of matter creates a gravitational well so deep that it influences the motion of galaxies hundreds of millions of light years away. The gravitational pull from this region is so strong that it overcomes the natural expansion of the universe in our local cosmic neighborhood. The challenge of studying something you cannot directly see required astronomers to become cosmic detectives, using indirect evidence to map the invisible. They studied the motions of galaxies they could observe, tracking their velocities and directions to map the underlying gravitational field. Like following breadcrumbs through a dark forest, each galaxy's motion provided clues about the massive structure pulling them along their cosmic journey. Understanding how galaxies move through space requires us to think beyond the familiar motions we experience on Earth. In our cosmic neighborhood, galaxies aren't simply floating randomly through space. They flow like rivers, following invisible currents created by gravity. These cosmic streams carry galaxies along predictable paths toward regions of higher mass density, much like how water flows downhill toward valleys. In 1986, a group of astronomers observing the motions of the Milky Way and neighboring galaxies noted that the galaxies were moving toward the Hydra and Centaurus superclusters. This discovery marked a crucial step in understanding our cosmic motion. Astronomers found that our galaxy and its neighbors weren't just drifting aimlessly through space, but were part of a vast, organized flow of thousands of galaxies all heading in the same general direction. Picture a massive river system viewed from space, with countless tributaries flowing into larger streams, which eventually converge into a mighty river flowing toward the sea. This is essentially what happens with galaxies on cosmic scales. Small groups of galaxies merge into larger flows, which join even more massive streams, all eventually flowing toward regions of concentrated mass like the Great Attractor. The velocities involved are staggering. Our local group, which includes the Milky Way, Andromeda, and dozens of smaller galaxies, moves through space at approximately 600 kilometers per second relative to the cosmic microwave background. To put this in perspective, at this speed, you could travel from Earth to the Moon in just 11 minutes. Yet despite these incredible velocities, the distances involved are so vast that this cosmic journey unfolds over hundreds of millions of years. Astronomers discovered that this motion isn't unique to our local region. Similar flows exist throughout the observable universe, with galaxies streaming toward various massive attractors. However, the Great Attractor stands out because of its proximity to us and its enormous influence on our cosmic neighborhood. By mapping these galactic flows, scientists began to understand the large-scale structure of the universe, revealing a cosmic web of matter connected by gravitational threads spanning billions of light years. As observational techniques improved, astronomers gradually began to peer through the cosmic dust and identify the actual structures responsible for the Great Attractor phenomenon. The breakthrough came when they focused on a region in the constellation Norma, where infrared and radio observations revealed something remarkable. Hidden behind the galactic dust was one of the most massive galaxy clusters in our cosmic vicinity. The Norma cluster is the closest massive galaxy cluster to the Milky Way and lies about 220 million light-years away. The enormous mass concentrated here and the consequent gravitational attraction mean that this region of space is known to astronomers as the Great Attractor. Imagine discovering a hidden metropolis behind a mountain range. The Norma cluster represents just such a cosmic city, packed with hundreds of large galaxies and surrounded by vast halos of dark matter. Galaxy clusters are among the largest gravitationally bound structures in the universe. They contain hundreds or even thousands of individual galaxies, all held together by gravity and embedded in enormous reservoirs of dark matter. The space between galaxies in these clusters fills with hot gas, heated to millions of degrees by the intense gravitational environment. This gas glows brightly in high-energy wavelengths, providing another way for astronomers to study these massive structures despite the optical obscuration. The Norma cluster, however, represents just one component of the Great Attractor region. As observations became more sophisticated, astronomers realized that this area contains multiple galaxy clusters, groups, and vast filaments of dark matter, all contributing to the total gravitational influence. It's like discovering that what you thought was a single mountain is actually part of an entire mountain range, each peak contributing to the overall topography of the region. The gravitational field created by this concentration of matter extends far beyond the visible clusters themselves. Dark matter, which makes up approximately 85% of all matter in the universe, forms invisible scaffolding that amplifies the gravitational effects. This dark matter doesn't interact with light, making it invisible to our telescopes, but its gravitational influence shapes the large-scale structure of the universe and guides the motion of galaxies across vast distances. The story of the Great Attractor took a remarkable turn in 2014 when astronomers made a discovery that revolutionized our understanding of our place in the universe. Using sophisticated mapping techniques that trace the flow of galaxies across hundreds of millions of light years, they discovered that our Milky Way galaxy belongs to an enormous structure called the Laniakea supercluster. The Laniakea supercluster encompasses approximately 100,000 galaxies stretched out over 520 million light years. To comprehend this scale, imagine trying to visualize a structure so vast that light itself takes over 500 million years to cross it. Within this cosmic metropolis, it has the approximate mass of 10 to the 17th power solar masses, or 100,000 times that of our galaxy. The name comes from Hawaiian, meaning immense heaven, a fitting description for this cosmic structure that serves as our galactic neighborhood. This study also clarifies the role of the Great Attractor, a gravitational focal point in intergalactic space that influences the motion of galaxies within the supercluster. Rather than being a mysterious external force pulling us toward an unknown destination, the Great Attractor represents the gravitational center of our own cosmic home. Think of the supercluster as a vast cosmic watershed. Just as rivers flow toward the ocean following the topography of the land, galaxies within the supercluster flow along gravitational currents toward its center of mass. The Great Attractor region represents the lowest point in this gravitational landscape, the cosmic equivalent of a valley where all the streams converge. This discovery fundamentally changed our cosmic perspective. Instead of being pulled towards some distant, alien structure, we're actually part of a vast gravitational family. The galaxies around us, including our Milky Way, are all siblings in this enormous cosmic structure, connected by invisible threads of gravity that have guided our dance through space for billions of years. Our motion toward the Great Attractor isn't a journey to a foreign destination, but rather a homecoming to the heart of our own cosmic neighborhood. The cosmic journey toward the Great Attractor unfolds on timescales that dwarf human imagination. To understand this motion, we must think in terms of cosmic time, where millions of years pass like moments and the stately dance of galaxies plays out over billions of years. Our local group's motion toward the Great Attractor began shortly after the formation of large-scale structure in the universe, when gravity started pulling matter together into the cosmic web we observe today. At our current velocity of over 1 million miles per hour, you might expect this cosmic journey to end relatively quickly. However, the distances involved are so staggering that this apparent speed becomes almost imperceptible on cosmic scales. The Great Attractor lies approximately 250 million light-years away, meaning that at our current rate of approach, we wouldn't reach it for many billions of years. To put this in perspective, this journey will take longer than the entire history of life on Earth. But the universe doesn't remain static during this long voyage. The expansion of space itself works against gravitational attraction, stretching the fabric of space-time and increasing distances between distant objects. This cosmic expansion, driven by dark energy, acts like a cosmic headwind that slows our approach to the Great Attractor. In regions where gravity is strong enough, like within galaxy clusters and superclusters, this expansion can be overcome, allowing structures to grow and merge. As we journey through space, we're also part of other cosmic motions. Our solar system orbits the center of the Milky Way every 230 million years, while the Milky Way itself rotates and slowly approaches the Andromeda Galaxy. These multiple motions combine to create a complex trajectory through space, like a cosmic ballet where multiple dancers move in intricate patterns simultaneously. The ultimate fate of this journey depends on the balance between gravitational attraction and cosmic expansion. Current models suggest that while we'll continue moving toward the Great Attractor for billions of years, the accelerating expansion of the universe will eventually halt and reverse this motion. In the distant future, the components of the supercluster may begin to drift apart as cosmic expansion overwhelms even the strongest gravitational bonds, leaving each galaxy to face an increasingly lonely universe. The Great Attractor phenomenon has become one of our most important windows into understanding dark matter, the mysterious substance that makes up approximately 85% of all matter in the universe. While we cannot see dark matter directly, its gravitational effects are written across the cosmic landscape in the form of galactic motions and large-scale structure. The Great Attractor region serves as a natural laboratory for studying how this invisible matter shapes the evolution of the universe. Think of dark matter as the invisible scaffolding of the cosmos. Just as a building's framework determines its shape and stability even though we cannot see it through the walls, dark matter provides the gravitational skeleton that holds together massive structures like galaxy clusters and superclusters. In the Great Attractor region, computer simulations suggest that vast halos of dark matter, each containing trillions of times the mass of our Sun, create the gravitational wells that trap and concentrate normal matter into the galaxies we observe. The distribution of dark matter in the Great Attractor region follows a complex three-dimensional web of filaments and nodes. These cosmic highways of dark matter stretch across hundreds of millions of light years, connecting galaxy clusters and guiding the flow of normal matter along their gravitational currents. Where these filaments intersect, we find the most massive galaxy clusters, like beads on an invisible cosmic string. Recent studies using gravitational lensing have begun to map this dark matter distribution directly. When light from distant galaxies passes through regions of concentrated dark matter, the gravitational field bends and distorts the light, creating subtle changes in the appearance of background galaxies. By carefully analyzing these distortions, astronomers can create maps of dark matter density, revealing the hidden architecture that drives the Great Attractor phenomenon. The Great Attractor also helps us understand how dark matter and normal matter interact during the formation of cosmic structure. While dark matter can only interact through gravity, normal matter can radiate energy and cool, allowing it to collapse more efficiently into dense structures. This difference means that dark matter forms the large-scale framework first, and normal matter subsequently flows along these gravitational channels to form the galaxies and clusters we observe. Understanding the dark matter connection has implications far beyond the Great Attractor itself. The same physical processes that created this massive structure operate throughout the universe, shaping the cosmic web on the largest scales. By studying how dark matter concentrates in regions like the Great Attractor, astronomers gain insights into the fundamental nature of this mysterious substance and its role in cosmic evolution. The discovery and study of the Great Attractor has profound implications for our understanding of the universe's structure and evolution. This cosmic phenomenon reveals that the universe is far more organized and interconnected than early astronomers could have imagined. Rather than galaxies moving randomly through space, we see evidence of vast, coherent flows that trace the underlying gravitational architecture of the cosmos. The Great Attractor, rather than anything to be afraid of, is where our local galaxies are heading to hang out, the central gravitational point of our local area of the universe. This perspective transforms our understanding of cosmic motion from something alien and threatening to something familiar and comforting. We're not being pulled toward an unknown fate, but rather flowing along the natural currents of our cosmic neighborhood. The study of the Great Attractor has also advanced our understanding of dark matter and its role in shaping cosmic structure. The gravitational effects we observe require far more mass than we can account for with visible matter alone. This invisible dark matter provides the gravitational scaffolding that holds together massive structures like Laniakea and creates the flows that guide galactic motion. Understanding these dark matter distributions helps astronomers map the invisible architecture of the universe. Furthermore, the Great Attractor phenomenon demonstrates how local gravitational effects can overcome cosmic expansion on certain scales. While the universe as a whole continues to expand, regions of sufficient mass density can resist this expansion and even contract under their own gravity. This balance between expansion and contraction shapes the evolution of cosmic structure and determines the fate of different regions of the universe. From a philosophical perspective, the Great Attractor reminds us of our deep connection to the cosmos. We often think of Earth, our solar system, or even our galaxy as isolated islands in space. However, the reality is that we're part of vast cosmic currents that connect us to structures spanning hundreds of millions of light years. Our motion through space isn't random or purposeless, but follows ancient gravitational pathways that have been shaping cosmic structure since the universe was young. And on that note, we conclude our journey through the mystery of the Great Attractor. We've discovered that what initially appeared as an invisible cosmic force pulling our galaxy toward an unknown destination is actually the gravitational heart of our own cosmic home, the supercluster that contains us. This enormous structure, spanning over 500 million light years and containing 100,000 galaxies, represents our address in the vast cosmic web. The Great Attractor teaches us that the universe is far more interconnected and organized than we might have imagined. We're not isolated wanderers in an empty void, but participants in a grand cosmic dance that has been choreographed by gravity over billions of years. Our Milky Way, along with thousands of neighboring galaxies, follows ancient gravitational currents toward the center of our cosmic neighborhood, a journey that will continue for billions of years to come. This cosmic phenomenon also highlights the remarkable detective work of astronomers who pieced together this story despite the challenge of studying something hidden behind our own galaxy's dust. Through ingenuity, persistence, and the use of multiple wavelengths of light, they revealed one of the most significant structures in our local universe and helped us understand our place within it. Thank you for joining me on this nocturnal voyage through the cosmos. Until next time, keep looking up at the night sky, knowing that you're part of something far grander than you might have imagined.